Hello guys, this is Ishan Akbar. In this video, we will discuss about the Hardy cross method to solve uh, loops in a water supply network or in a pipe network system. So basically, this is an just an example or a pictorial view of the pipe network provided for housing societies or colonies to distribute water from the source to the housing points or homes or commercial areas or residential areas. To distribute water from the inlet to the outlet points, we need a network of pipes. This system of pipes or this network of pipe will get some supply from this inlet and will supply from at these points. These are known as outlets. If we supply 100 liter per second water at the inlet, we will have 100 liter per second. We will have a sum of 100 liter per second at the outlets, but this is not necessary that here it will go 50. Sorry, if we need 50 liter per second here, we have to distribute this 100 through these pipes in a technical manner. To distribute this flow within this pipe system, we need to know the Hardy cross method, because Hardy cross method is basically used to distribute the flow within the pipe network. It has nothing to do with the inflow and the outflow. It just will distribute the coming inflow within the system with each pipe and will shift it to the outflow points. And if we move towards a pictorial view for a, let us say we have a housing society, and in this housing society, we are going to design a water supply system. Water is coming from this direction. This is inflow point, and we will need some water at this point. At this point, we will have different outlets at different points. So we'll need to distribute this inflow along these pipes. All the blue pipes you can see here, we will need to distribute this inflow in these blue pipes using Hardy cross method. So basically, you can say that Hardy cross method is applied to distribute flow rates within pipes of a pipe network or a distribution system. But for Hardy cross method to apply, we basically need closed loops. So here you can see that this is a closed loop of pipes. There may be three, four, minimum three pipes, and maximum we have no idea that how many maximum pipes can be there in a closed loop. So moving with the procedure, we have five different steps to follow the Hardy cross method. Uh, the first and most important step is to assume a most reasonable distribution of flows that satisfies condition one. There are three conditions basically. The condition one is Q is equal to AV. It means that our pipe network system will follow the equation of continuity, mean at a joint, coming discharge and outgoing, incoming and outgoing discharge must be same, following the equation of continuity. And second point is condition number two is, this is condition number one, that our flow must follow the continuity equation. Condition number two says that friction laws are valid during this movement of flow within the pipe network. And condition number three says that summation of head losses in a loop must be equal to zero. In a closed loop, that's why we call it as closed loop system. Why? Because we will need to get the head loss summation within the loop equal to zero. And the second step will be, we will have some factors like K. K is basically depending upon the length, diameter, and friction of the pipe material. Length of the pipe, diameter of the pipe, and friction of the pipe material. There are two methods to estimate or find out this K. It can be estimated using two formulae. First one is the Hazen-Williams equation, and the next is Darcy-Weisbach equation. In Hazen-Williams, the value of K is L times 10.67 divided by C raised to power 1.85 and D raised to power 4.87. And for Darcy-Weisbach equation, K is equal to L times 8F divided by G pi squared d raised to power 5. You can use both of them depending upon the requirements. But most of the cases, this is this Darcy-Weisbach equation is the favorite one. So K is this one. If we have F, L, and D given with us, then we can determine the value of K by putting these values here in this formula, L, F, and D. And Q is discharge assigned to this. From step 1, we will get the Q for each pipe, and K will be obtained from here, and N is the value which is given as 2, because here in Darcy-Weisbach equation, head loss is related to Q as a square power. And in this Hazen-Williams equation, HF is relevant to discharge with a power of 1.85. So in Hazen-Williams equation, N is 1.85, but in case of Darcy-Weisbach equation, it is 2 for a turbulent flow. So a first step is assigning the discharge to a pipe, and the next type is finding the head loss in a pipe. If we have five, six, seven, or eight pipes in our loop in our pipe network system, we will find out the head loss in each pipe. Mean we if we have nine pipes, so we will have to calculate the nine head losses in the pipe network. The step three involves finding out the summation of head loss. If we have we will distribute basically the system in loops. If we have a pipe system like this one, so we have four loops, one, two, three, and four. So we will first ponder on the first loop, then second, third, and fourth. For first loop, we have three pipes, this one, and this one. We will calculate head loss of pipe 1, head loss of pipe 2, and head loss of pipe 3, and then we will calculate the summation of head losses like this. Summation of head loss is equal to summation of head loss of pipe 1, head loss of pipe 1, head loss of pipe 2, and head loss of pipe 3. But here we will follow the direction that we will form a loop like this one, and then we will draw a clockwise direction arrow with a positive sign. This is a sign convention that clockwise direction is taken positive in this loop in case of Hardy cross method, and counterclockwise direction is taken as negative. So this is negative direction. When we will be distributing discharges, we will see in the example, then we will have some specific direction of movement of discharge, like this one. So this is positive movement. This is also a clockwise direction in this loop. Within this loop, we'll see in this loop. So if we want to move the flow of this pipe in this loop, so it will move in this direction, in this circle. So this will have a clockwise direction. So its head loss will be positive. If this is first pipe, head loss 1 will be positive. And for this, how the discharge of this pipe will move in this loop, it will move in this direction. So it will be also positive because this is positive. And if we call it as second pipe, so it will be HL2 will be also positive. And for third loop, this discharge will move in this direction. It is counterclockwise, it will be negative. So we can say that HL3 is negative here. In this way, we will add up. It means we need the value of head loss with the directional impacts, with positive or negative sign depending upon the clockwise and counterclockwise rotation. In a rare case, you will get the summation of head loss equal to 0, but at the first attempt or with the first attempt, it is not possible to get the answer of summation of head loss is equal to 0. When you get the answer, it will not be 0 at the first instance. By good luck, you can get the answer or summation of head losses in clockwise and anti-clockwise direction in a loop 0. But in every case, it does not happen. It will happen in rare cases. So you have to get ready for the next step, that you have to apply correction. So what will be correction? If head loss is not equal to 0, it means Hardy cross method says if this is not equal to 0, summation of head loss, then you will have to move towards the correction. So step 4 says that you have to apply some correction to already assigned discharges in the loops. So this correction delta Q will be obtained by this formula. Simply if we write n, the value of n in our case is 2 because we are using Darcy-Weisbach equation, and in this n is equal to 2. And now, basically, it is this formula is summation of head losses divided by summation of k q naught into n. N means 2, and here power is n minus 1, 2 minus 1 will be 1. So again, we will divide this by 2k q naught, summation of k q naught, and multiplying it with 2, or you can say that summation of 2k q naught for each pipe in a loop. You will simply add up the head losses in the pipe loop in a single loop, and put the value here. It may be positive or negative depending upon the direction, and the positive value of this summation of 2kq naught for a loop, and if you divide these two values you will get a correction. This delta q means a correction that will be applied to the specific loop 1 2 3 4 5. So if we are moving with the first loop, then this correction will be for first loop only. If we move towards second loop, we will repeat the same steps for second loop, and if we are moving towards third loop, we will repeat the same steps for the third loop. We will do a question or example to understand the procedure effectively. Now, the last step is to apply the correction. If this is very important thing, if summation of hl is positive, it means that clockwise discharge is more, because we assign hl a positive sign when it is clockwise direction, when q is in clockwise direction. So if hl comes in positive value, it means that clockwise movement is more, so our approximation is more basically. So we need to reduce it. How? By how much amount? By delta q. Mean, if we have assigned a discharge q1 to a pipe, now this will be reduced by delta q. Delta q will be subtracted by from q1. And if delta hl is negative, it means that counterclockwise q is more, that discharge in counterclockwise direction is more, so we will have to reduce it by an amount of delta q. So in delta HL, if delta HL is positive, counterclockwise Q is more. It means that count clockwise Q is more, and in the same way, counterclockwise Q is lesser. So we want to increase it by how much amount? By the same amount clockwise discharge is reduced. And if delta HL is summation of HL is negative, counterclockwise Q is more, it means that clockwise Q is lesser. So what will we do? We will simply increase the clockwise moments by how much amount? By the same amount delta Q by which we reduced counterclockwise Q. So we have an example here that there is a distribution system containing 5 pipes with an input supply of 90 liter per second given at A, supplied at A, and we will have been taking off this discharge at 3 points B, C, and D. As at B we need 30 liter per second, at C we need 40, and at D we need 20 liter per second. This is basically in liters per second. So, as per my knowledge, you can do anything. You can assign any values to any pipe, no problem. But if you take rough assignment or rough ideas, your number of trials may increase. Just this will happen. Otherwise, you will solve the question correctly after the last attempt. So I have distributed roughly that this pipe will be taking 50 liter per second and this will be taking 40. 50 plus 40 comes 90. At A we have 3 things. First one is the incoming, and two are taking away the flow. This is taking 50 away from A, and this is taking 40 away from A. So this 40 will reach at this point, and it this 40 will supply this 20 here, and 20 will be available here. And this 50 will reach at B, 30 will be taken off out of the system, and remaining will be 20. So we say that this 15 is supplied. This is just my idea, my distribution. You can change this, no problem. So from this remaining 20 at point B, because 30 is taken off from 50, 20 remains at this point B, 15 is taken towards C, and 5 is taken towards this D. So this will be like this one, this distribution. So we have to be very careful while assigning arrow directions, because sign of HL will depend upon these arrows. When this 5 will reach at this D point, 20 is always available, and this 5 will mix with this one. It will become 25. There is no other direction, so it will move in this direction to be at this C point. This 15 coming from this side in pipe BC, and this 25 will mix at this point. 15 plus 25 makes 40, so demand of C will increase. It means that we are following the equation of continuity while distributing water in the water supply network. With this initial distribution, following the first step, we have done with the first step. We are done with the first step, as we have assumed the most reasonable distribution of flows that satisfies condition 1, means we have satisfied the equation of continuity at each point, at each joint, because at this A, coming flow is 90 and outgoing flow is also 90, 50 and 40. At this D point, we have two coming flows, 5 and this 40. 45, 20 is going this way and 25 this way. So 25 plus 20 is 45. And at this C point, 15 is coming from this direction and 25 in this direction. 40 is coming out. And at B, we have 50 coming, 20, 30 is going out, and 5 is in going in that direction, and 15 is going in this direction. So 15 plus 5, 20, 20 plus 30 will be 50. So it is following the equation of continuity. Now, we have 5 pipes. So basically, we can make two loops. Loop A, this loop will start from this point, will move to B, and then at D. A, B, D. Loop will be from a single circular path. Loop will be assigned that will have a single circular path or movement of water within pipes with no crossing. Mean there is no crossing between these pipes. There is no any other pipe connected. If let us say we have a pipe here, somewhere here, so there will be two loops, one this one and other will be this one. So there is no crossing of any other pipe, so this is a triangular loop here. So we will draw a clockwise direction to see the positive direction, and here this will be the loop 2. This is loop 1, and this is loop 2 with positive clockwise direction. So in this question, we have two loops. We may have different types of loops. And let us say we have this system. In this system, we have this one loop of non-intersecting pipes. This is second loop, third, fourth, and this is fifth loop. So we have 5 loops in this case, but in our case, there is only 2 loops. So moving with these assumptions, or these assigned discharges, assumed discharges, we will move towards the trial 1. So trial 1 will carry on the uh, different pipes. Let us assign the names to pipes. This is pipe 1, pipe 2, pipe 3, 4, and this is pipe 5. Well, simply in loop 1, this is loop 1. In loop 1, clockwise direction is taken as positive. So what is q of each pipe? In loop 1, in this loop, ignore this one. Just ignore the second loop and consider on ponder on the first loop. So in first loop, first pipe is here, and we assigned 50 liter per second discharge to pipe 1. What is this discharge of second pipe? Irrespective of the dimension, just write the amount of discharge. And what is discharge of pipe 3? This is 5. And what are the values of k? These are given as r. This is basically k. These values are, wherever you see r, basically r and k are replacements of each other. So k for first pipe is 2, second pipe it is 4, and for third pipe it is 1. Now we have to find the head loss for each pipe. K into q square. This square comes from the Darcy-Weisbach equation. K is 2, q is 50. 50, we will take the square of 50, it will be 2500, and we will multiply it with 2. It will be 2 times 50 square, it will be 5000. And now 4 times 40 square, this will be 6400, and this will be 1 times 5 square, this will be 25. So now we have to assign these symbols. When we get the value of HL, we just need to assign the symbols. Either it is positive or negative head loss. So just see the direction of flow. This is moving in this direction, this is moving in this direction, this in this direction. We have three pipes in this loop. This is loop 1 for trial 1. This is clockwise direction. Clockwise is taken as positive. So we can say that clockwise is positive and counterclockwise is negative. So this is clockwise because this discharge 40. If we consider just this loop, so this discharge will move in this direction through this loop. So it will be positive. So 5000 is, sorry, for this first. Okay, go with the second pipe. Second pipe will have a clockwise discharge, so it will be positive. Now, for the first pipe, what will happen? Its discharge will move in this direction within this loop. It will move in this direction. So this arrow shows the direction. You can see the arrow and then curl it in the required direction. It will be in anti-clockwise direction. So it will be negative. And for the same, this will also have a counterclockwise impact or counterclockwise movement in this. Just consider the single pipe by ignoring the discharge from the other pipes in the loop. For the third pipe, if we say we have discharge of 5 and moving in this direction, so what will be the direction of movement of this discharge in this loop? It will move in this direction. It means that it will move from B to C, D, then D to A, and then A to B. So its direction is this one. And if we ignore this and follow the first pipe, so how it will move? It will move from A to B, B to D, and D to A. It will also follow an anti-clockwise direction. So it will be also negative. Now, just sum up these values with signs. Minus 5000 plus 6400 minus 25. When we sum up these values, it comes to be plus 1375. 1375, and it means that HL summation of HL is not zero. In the steps we studied that we need the value of HL equal to 0. But in our case, it is not 0. It means we need the step 4, which is the correction. We have to apply the correction. So for correction, we need 2kq. 2 times k for the first pipe is 2. And what is q here? This is 50. So it will be 200. 2 times 4 times 40, 320. And 2 times 1 times 5, it is 10. We will simply add these values. This will be 5 30. Now we need to get the corrected Q value. This 1375 suggests that we have to apply the correction because it is not equal to 0 or near to 0. So what will be correction? It will be delta Q, and the formula for correction is minus summation of HL divided by summation of 2KQ. What is summation of HL with minus sign? This is 1375 and divided by 530. So value of delta Q is 2.6 minus 2.6. So we have a correction of 2.6. What will we do with this one? This HL will let us know that what to do with this 2.6. As we'll write a statement as summation of HL is positive. What does this mean? Because we are taking clockwise movements as clockwise head losses or discharges as positive, and HL has a positive value. It means that clockwise Q is more, mean positive discharges are more. Therefore we have we have a net answer of positive for HL. So we need to clockwise Q is more. So what can we do? We have to reduce it. How much? 2.6 liter per second. So where we see HL positive, you have to reduce it. It is 40. You will simply do 40 reduced by 2.6. So what will be the value? It will be 37.6. Now, what will happen to counterclockwise movements? It means that counterclockwise Q is lesser. That's why the value of summation of HL is positive. So we have to increase it. All the discharges, all the counterclockwise discharges will be increased and all the clockwise discharges will be reduced. So we have this counterclockwise discharge, this is clockwise discharge which is reduced, and this is also counterclockwise because here we can see the negative sign. We will apply changes, we will apply correction on discharges, not on the head losses. These will just guide us that where to add the discharge, where to increase the discharge, or where to decrease the discharge. Correction will be applied to the discharge already assigned to the pipe network. So this will be increased because HL has negative sign here by 2.6. This will be 52.6, and this 5 will be reduced by increased by 2.6, increased by an amount of 2.6, 7.6. It means that we have now new discharges for these pipes, for these three pipes. It means that in next we can write new values of the discharges, that for first pipe we have 52.6, for this we have 37.4, and for this we have 7.6 values. But for the case of next loop, we will keep see this green pipe. Basically, this pipe is a shared pipe between both loops. This pipe is a part of first loop as well, and it is also part of second loop as well. So this pipe will have two corrections, mean from loop 1 and from loop 2 as well. When we are considering or drawing the loop 2, we will have to draw this pipe as well. So it will have a discharge of 5 till now. So for pipe 3 we have a discharge of 5 before the correction, because we have not applied the correction to hold the system, we have just applied to the loop 1. So we will just need this value to be in this table. For fourth pipe, this was the fourth one, the discharge value is 15. For fifth pipe, the discharge is 25. K values are 1, 1 and 2. 1, 1 and 2. What is HL? As we calculated for the loop 1, it will be K Q square. K is 1 and Q square is this one. It will be 25. It will be 225 and it will be 1250. 2 into 25 square. 25 square is 625 times 2 is 1250. So now we have to assign signs to the values of HL. What is clockwise in this system? If we want to know the this shared pipe 3, what is its arrow? It's going upward, left upward. So if we want to know the movement of flow of pipe, shared pipe or this third pipe, then loop 2 only it will move in this direction. So what is this direction? This is basically clockwise direction. So it will be positive. And 225 fourth pipe, this one, moving this way, it will have counterclockwise direction this way. So it will be negative. And for this pipe, we have this arrowhead. So it will be also in clockwise direction. It is positive. So we'll simply add up the values of pipe 3, 4, and 5. These are basically names of pipe 3, 4, and 5. So we'll simply add the values of HL of all the pipes to get the net answer. It will be plus 1050. Again, the HL is positive. It means that clockwise discharges are more as compared to counterclockwise discharges. Now, it is not 0. It means that we need to apply the correction. For correction, we need 2 into K into Q. This is 10. In the same way, for fourth pipe, it will be 30. And for this pipe, it will be 100. So it will be equal to 140. So we need corrected Q. So this is summation of HL divided by summation of 2KQ. What is minus into HL? It is 1050 divided by 140. And delta Q is equal to minus 7.5. What does this mean? It means that we need a correction to each pipe in the loop with a 7.5 value. Each pipe will have a correction of 7.5 liter per second. So where it will be adjusted, in which pipe this 7.5 will be added, and from which discharge it will be subtracted. This depends upon the sign of summation of HL. As the sign of summation HL is positive, this one, it means that clockwise Q is more. Again, so what to do? Reduce it. Reduce the clockwise discharges. We have two clockwise values, this one and this one. This plus shows the clockwise value. We will adjust these values. So this is the important point. Pipe 3 is a shared pipe. We have already applied a correction for after which we had a discharge of 7.6. So we have to apply a correction on the previously corrected value of this one. In this table we will write the original value 5, but when going to apply the correction you will apply it on the corrected value. So because this is positive, this is clockwise, we have decided this positive, it is clockwise, so we will subtract this 7.5. Just keep an eye on this 7.5. Don't consider this negative sign. So subtract this from clockwise moments and add this 7.5 to counterclockwise moment, which is 15. So it will be 0.1, it will be 22.5, and it will be 17.5. So now we have corrected values for both the loops, for loop 1 and loop 2. Now the final discharge of the pipe 3, this is pipe 3. It is not 7.6, it is basically 0.1. So we'll write the values in the trial 2. 52.6 for first pipe, this one. because we are moving again to the trial 2 with the first loop again. 52.6, 37.6, but we will not write this value 7.6 for the shared pipe because it is zero point 0.1 after second correction on the second loop. So it will be zero point 0.1 and 37.4. Now, moving again with these discharges, it is not, we are not sure that our distribution after the first correction or after the first trial will be okay. We have to check it again. If it will be okay, this value of this HL will be near to zero. And if it is not near to zero, so we need another correction. We will have a correction for the second time. And we will keep applying the corrections until we get the answer of delta summation of HL approximately equal to 0. Otherwise we will continue till 10, 15, or so many trials, but it will take 3 to 4 trials to adjust your answer. Okay, so what will be the value of HL by using this KQ square formula, using these Q values, because we have now Q values for three pipes, these values. And directions of these value are assumed from the last discharges because all the discharges were positive. In this, discharges are positive, so all these directions are correct. And from for loop 1, all the discharges were positive, so it means that our original directions are correct till now after the first trial. So in trial 2, we'll move towards the HL for the first pipe. It will be double five double 3.52. For the second pipe, it will be double five 95.04, and for the third pipe, it will be 0.01. So, which value will be positive and which will be negative, it will be decided through this loop. This will be counterclockwise, this will be clockwise, and this will be counterclockwise. It means just this value will be positive. Pipe 2 will have a positive value, and other both values will be negative. This is clockwise, and these both are counterclockwise. So if we take the sum of all three values, it will be plus 61.51. And it means that we are not getting the summation of HL, mean sum of head loss within the loop 1 is not equal to 0. It means that we still need the correction to be applied to loop 1 or pipes, three pipes of loop 1. Yes, but we are moving closer because in first case, in first trial, the summation of head loss was 1375, and now it is reduced to 61.51. It means that we are moving in positive direction. And now we will find 2KQ, 2K2, and Q is this 52.6. It will be 210.4, 299.2, and zero point 0.2. No need to consider the direction for this case. And now we will get delta Q, summation of HL divided by summation of 2KQ. So its summation will be equal to 509.8. So just put the values 61.51 and 509.8. Delta Q will be equal to minus 0.12. So we have to apply a correction of 0.12. How delta HL is positive or negative? It is positive. It means that we have to subtract this value of 0.12 from clockwise discharges, and we have to add this value 0.12 in the counterclockwise discharges. So simply, 52.6 is in counterclockwise direction, so we need to increase this. 52.6 plus 0.12, it will be 52.72. This is plus value clockwise movement, clockwise discharge. It means that it will be reduced 37.4 minus 0.12, it will be 37.28, and this zero point 0.1 will be increased because this is counterclockwise. This will be 0.22. So we have got the new discharges for loop 1, but keep an eye on this value because this is a shared pipe. This pipe 3 is a shared pipe between the two loops. It is connected with the first loop and also with the second loop. So moving towards the second loop, I have written the discharge. So for each trial, you have to write the discharge as we got from the last trial. Zero point 0.1 with the shear pipe and zero point 0.1 with the in the loop 2, which is also available. This pipe 3 is also available in loop 2. So we have written the discharges after trial 1, 0.1, 22.5, and 17.5. Now we will have HL, value of HL head loss for each pipe. The values of head loss for each pipe will be 0.01, 506.25, and 612.5. And assigning the direction in loop 2. So what is the direction of this one in this loop? This is counterclockwise. So it will be negative. For fourth pipe, this is fourth pipe. So it will be counterclockwise negative. And for, sorry, this is clockwise movement. This is positive, and fifth pipe is also positive, and fourth will be negative. So taking the summation of these values, it will be 106.25. In the last case, during trial 1, we got it as 1050. It means delta HL is now reduced for second loop as well, 1 to 106, but it is a positive value. Now it means that HL summation of HL is not equal to 0 or not near to 0, so we need a correction. So we will apply 2kq, it will be 0.2, and again for this one it will be 45, and it will be 70. So we need the summation of these values will be 115.2. Which we need a correction factor, it is summation minus summation of HL over summation of 2kq minus 106.25 divided by 115.2. So delta Q will be equal to minus 0.92. It means that we need to apply a correction of 0.92 to each pipe of second loop. But take care while applying on this shared pipe because this pipe is already corrected with a value of 0.22. It means that you have to write a separate value of 0.22 for this pipe in the loop for just corrected Q, not for this purpose, for this column. So because again HL is positive, it means that clockwise Q is more. If it is more, we need to reduce it. And delta H is positive, it means that counterclockwise Q is lesser, so increase it simply. So where you see the negative sign with HL, you have to add this 0.92 to the discharge, 22.5 plus 0.92, and we have to subtract from the other values. Just do not take this zero point 0.1 for correction, to take 0.22 for correction because it is already corrected in loop 1. 0.22 minus 0.92, because this has a positive sign, it means that this is clockwise discharge. 0.1 is clockwise discharge, and correction will be applied to 0.22 minus 0.92 and 17.5 minus 0.92. So the final values will be minus 0.7. Here we have got a negative value of discharge, which is impossible. So what is the impact of this negative value? We'll see in the next phase. Now, this will be 23.42, and this will be 16.58. So these are corrected values after trial 2 for the both loops. Now we will move towards the trial 3 and we'll check that either we need the correction or not. So we'll simply write down this discharge after first correction. So the loop 1 after first correction had a discharge of 52.72, discharge 1, pipe 1, and for pipe 2 it was 37.28, and for pipe 3 it is 0.22. Is this okay? No. After second correction, for pipe 3 we have a value of 0.7. So it means that we need to revise and write it as minus 0.7. So it will be minus, it will not be 0.22, it will be 0.7, but in the opposite direction. This minus sign indicates that you have to change the direction, assumed direction, because this assumed direction is not okay. So this pipe will have a discharge in this direction, coming from top to bottom and coming from left to right. It means that it is moving towards right bottom or bottom right. Now again we will calculate the values of HL. We will calculate the summation of HL here. We will calculate the, if this is not equal to 0 or near to 0, we will again apply the correction, that is delta Q equal to minus summation of HL divided by summation of 2KQ. In the same way as we applied during the last two trials, trial 1 and trial 2, moving towards the same two loops, loop 1 and loop 2, we will be applying all the corrections, and we will be moving until we get the answer of delta HL approximately equal to 0. It means that you can sum up the HL approximately 0.02, 0.01, or this way. If we get an answer of 0.01 or 0.02 for delta HL, it means that our system is okay and our final distribution of discharges will be written like these values: 0.7, 34 or 23.42, 16.58, 52.72, and this was 37.28. This may take 3 or 4 trials to complete your question. So this is all about the Hardy cross method for pipe networks. Thank you very much. See you in the next video. Allah Hafiz.